So, this little guy, let's kind of recap a kind of a big picture bonding things and how they relate to IMFs. Kind of recap that. That way tomorrow we'll spend more time finishing up our unit review and less time reviewing with me. So nomenclature, I think I reviewed as much as I can. I think the rest is on you guys to really remember some of the polyatomic ions and practice that. There are tons of nomenclature videos and other things online for you, okay? So these are some interesting concepts to think about whenever you are talking about bonding. Take notes where you want. There's one or two more things at the end that we've not learned, so that we want you to write that in. This right here, first of all, how can you talk about molecules, polar or nonpolar? You're considering both this and its overall shape, right? So this is basically saying, let's go with water. What is water? Draw the Lewis style model for water. What's your first step? Hold on, very, very first step. Count the valence electrons, right? Okay, so for water, count the valence electrons. 1 plus 1 plus 6 is 8 valence electrons. Okay, so 8 valence electrons, and then tell me what you're going to say next. Okay, so I'm thinking you're saying this, right? And then what? So lone pair here, lone pair here. Okay, so visualize that in your head. You're like, okay, got oxygen metal, 2 hydrogens, lone pair, oxygen's got octet, hydrogen's fine without octets, it's tiny. What shape is that? Can you visualize that? It's actually bent. It is not linear. The lone pairs do not actually sit on north and south. They actually move themselves and they bend the hydrogens down. So instead of looking linear, I'm going to go ahead and draw it like it's bent. Okay, and I want you to tell me, is the northern hemisphere negative or positive? More partially negative, partially positive. Partially negative, right? There's like some lone pairs up in there, and these are partially positive. So you should see that it's polar because it's like at an opposite end, opposite poles kind of deal to it, right? So we already knew water's polar. That's like common knowledge. Waters are polar or solvent. What does that tell us? That water and water, if these two waters were close to each other, what would they be doing with each other? Kind of intermolecular, between molecules, forces would they have? There are 3 of them. Name them for me. Dipole-dipole, London dispersion, and hydrogen bonding. Which of the 3 does water undergo? Hydrogen bonding. Not because it has a hydrogen, because that means lots of things have hydrogen, but because hydrogen's bonded to fall line, right? F over N. In this case, O. So the positive nature of hydrogens attracted to those lone pairs of oxygen. So that's called hydrogen bonding. So if I had you draw this, you're going to have to draw it like this. Okay, draw water, and draw a hydrogen bond, which is just dashed lines between the 2 parts of water that would attract to the other side of water, right? So oxygens and oxygens are not going to attract to each other. It's the partial negative region of one and the partial positive region of the other that would attract to each other. All these other things, can you tell me, these are all diatomics, right? I2, Br2, Cl2, F2. Are all of these molecules here polar or non-polar? You got a 50-50 here, right? Non-polar, so thank you, be loud and proud, right? So it's like same. So it's basically the same on either side. This is a linear structure. There's an equal distribution of electrons. There's no poles. I can keep going. It's non-polar, okay? So if it's non-polar, what is the only IMF it will have? London dispersion forces. So these little dashed lines here, which are the weak intermolecular forces, those are the LDFs, the London dispersion forces. Okay, so comparing hydrogen bonding, which is a stronger IMF, to London dispersion, which is a weaker IMF. If I had them both sitting here, and I was like, okay, I put a little heat on them, they're going to start to melt. They're going to maybe start to melt or evaporate. Who's going to evaporate or boil first? Something with London dispersion. So boiling first means lower melting point or lower boiling point. So these guys would probably boil first. Well, fluorine is the gas. Chlorine is a gas. Both of those have already boiled because they're already to their gaseous state. So what you should kind of glean from this is that the weaker the IMF, the more likely it is at a gas at room temperature. Okay? So weaker IMFs usually mean gases at room temperature. So you're using your logic. What do you think we could maybe assume about stronger IMFs? Maybe so, right? So stronger IMFs maybe would be liquids or solids at room temperature. It depends. Well, what's water room temperature, guys? What state of matter? Liquid, right? So that IMF being hydromonic makes it essentially a liquid. But we have this gray area in between, where actually, at room temperature, iodine is a solid and bromine is a liquid. Those are because their London dispersion forces are so strong, because they have so many more electrons than the chlorine and fluorine. Because not only do they have their valence shell, but they have all those inside shells. I mean, iodine's got what? 53 electrons, bromine's got 35, chlorine's got 9. So there's no comparison there. So sometimes this doesn't fit our mold because of the molar masses or because of the number of electrons. But what you should be able to say is that you can use IMFs to kind of determine the states of matter. So that's one fact we've not known. We kind of did that. There's hydrogen bonding. Ooh, ah. Ooh, ah, thank you, okay. So last thing is, how do IMFs play into solubility? So this is the last part we've not talked about. Sometimes we have to look at something and tell us, is it going to dissolve in water or is it not? What kinds of things definitely dissolve in water? That's just in everyday life. Salt is a very generic term. It means ionic compound. Give me its name.
Sodium
chloride. Because if not, I'm going to start going, okay, MATT, let's go here. You're like, all right, LOW, no. Try to say its name. Sodium chloride. You know that sodium chloride, or anything ionic, will dissolve in water. But there's some other things that will dissolve in water, too. Water, again, is that polar or non-polar? Polar, right? So you get yourself. So you know that water is definitely polar. The rule is like dissolves like. So if you don't write anything else down, write that down. Like dissolves like. And what I mean by that is polar things, polar solvents dissolve dissolve polar compounds. Yes?
Could I please have Abigail Huffman for dismissal?
Yes, thank you.
Thank you.
I'm videoing her house, so it should be up. So like dissolves like means polar things dissolve polar things. And guess what? Nonpolar things dissolve nonpolar things. So things like, can I go to the next page? I'll give you a second. Okay. So example, what would dissolve in water? Give me a compound that you know is polar based off its Lewis-Dot diagram. Okay, I know water, but I want something in water. Something to dissolve in water. Give me a Lewis-Dot model. Think back. NH3, do you remember this guy? NH3 is N with HHH and a little lone pair on top. That lone pair makes it partially negative. The H's make it partially positive. So it's polar. So ammonia, I mean, you can totally draw it. Don't get me wrong, you could draw that. But ammonia will dissolve in water because they're both polar. What would definitely not dissolve in water? Something nonpolar. Give me something nonpolar. Good job. Yeah. Carbon dioxide will not dissolve in water. So will not be something like CO2 because it's nonpolar. What about those diatomics we just had? What were their formulas? The diatomic ones. Like F2, Cl2, Br2, oops, 2, I2, they're all nonpolar. So are they going to dissolve in water? No. So the rule is they won't. But what could they dissolve in? What's something that's a nonpolar solvent? Oil. Oil, very good, guys. It's a nonpolar solvent. So it will dissolve things that are nonpolar. You can tell that they don't mix. This is water in blue, this is oil in oil color. They don't mix because they're not the same kind of compounds. I can make them look like they mix, but they're a lot alike. They just go back to normal. So what we're going to see is that if I had maybe like carbon dioxide or fluorine or chlorine or bromine iodine, they would dissolve in oil. And they would be one big, huge, mixed up kind of no heterogeneous mixture there, okay? So let's look at my picture. Oh, here's the like dissolves like. There's another example. I'm going to show you my video before I show you a picture, okay? This is my favorite video of all time. Have I shown you guys this? Of all time. Have I? I don't want to spoil the surprise. Okay.
Great, now we're getting sued by ACDC. The salt is up the water in the beaker today. The ions break apart in the usual way. The molecules of water get the ions apart. A salt solution formed, but that's only the start. Homogeneous, the same throughout. Homogeneous, the same throughout. Solids that are polar can dissolve. Solutes that are polar or ionic, that is really cute. Water and nonpolar science just won't mix, but a nonpolar solvent like an E can't mix. Like dissolves light, polar and polar. Like dissolves light, nonpolar and nonpolar, and all the stuff.
You, right? Polar and polar, nonpolar and nonpolar. You will not forget this.
Solvent molecules used up, better stuck with the solute ion in your cup. Solutions that are rated in a school for sure. Scientifity's been used for ever.
This is another unit. I literally needed the first 30 seconds of that. Okay, so that's our, well, hold on. That is our like dissolves light cup. And here's what it really looks like. Actually, I got this one for you. This is in like French.
When an ionic substance such as sodium chloride is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion.
Okay, this is what I need you to draw too, okay? We have, so this is sodium chloride, right? What's that green one right there? Say again? What's the green one? Who gets the negative charge here? The anion, right? The anion is chloride. Okay, Cl1 minus is chloride. The, what color is this? White? This little white one over here is who? Who's the white one? That's the ion, the white plus one. Sodium ion, right? Okay, so we have sodium chloride, and it was a structure, all lattice structure altogether. And then we put it in water, and the waters attack it and rip it apart. Okay, it's brutal. But what is the, if I draw water, what am I pointing towards the chlorine? Which side of water? The hydrogens, right? So the H's get attracted to the chlorine. I'll draw two of them here to say like they're teaming up on it. Okay, and what's attracted to the sodium? Oxygen, right? So the oxygen, simply because opposites attract, and the partial negative and partial positives of the water is attracted to the full-on negative and the full-on positive of the sodium. And so the water molecules team up. You can see it's surrounded by 3 or 4 in each of these cases. They're actually surrounded by 6, but that's essentially what we draw to support the case that water can dissolve ions because they have such a good attraction to them. Water is polar, and that's what causes this attraction. If something is nonpolar, it would not be able to dissolve.
On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Oh, that was fun. Okay. Let me see here. Stop that. Okay, one more thing, guys. I told you it wasn't very much here. Oops. Transparent background. Didn't mean to do that. Ugh. Take it back, okay. Alright, so the terms that go with this, you know, I kind of said it earlier, so they don't mix, that's called immiscible. We kind of already knew that term. Immiscible. I-M-M-I-S, this guy. So if things do not mix, it's called immiscible. Can you guess what it's called when they do mix? Miscible, right? So we're using some terminology I do believe you're familiar with: solvent, solute, and solution. Solvent is the thing like the bigger quantity, usually water in this case, or a nonpolar solvent, like benzene. Chem fix. Excuse me, sorry, a solute is what we're putting in the solution. So the solute might be like a little bit of salt, or like a sodium chloride kind of deal, or anything that's in smaller quantity that we're putting in. So we've got three terms: solvent, solute, which I don't have on the board. This is usually a smaller quantity. And solution, SLO, that's my abbreviation for solution. So based off of the context here, CH4, ooh, we know how to name these. What's CH4, guys? This is an organic compound. It's got one carbon, like we're playing charades. And there's 4 hydrogens. One carbon, what's the prefix for one carbon? Starts with the M, but not mono. You don't do this drug. Meth, okay. Meth, and what's the ending if they're all single bonded? Ane, okay, methane. This is cow farts, okay? Just know that. So methane is the CH4 compound. Ooh, what's ethane? Ethane, again, is also nonpolar. C what? C2. H6, because it's 2M plus 2. So 2 times 2 is 4 plus 2 is 6. Okay, it's like so last week, right? Okay. One more thing for you. If I were to say, okay guys, which of these would dissolve in water, which of these would not? First of all, this is NaBr, name that. So sodium bromide, is it ionic or covalent? Ionic, do ionic things dissolve in water? Yes, absolutely. We just drew it. So what does this look like in water? It looks dissolved. What's that look like? Okay, in water. What does one of the ions attain for its charge? Okay, I'll start you off. It's Na. And what's its charge? Positive 1. You guys are killing me today. Okay, bromine gets a negative 1. Okay, that's what it looks like. They're not bonded. Okay, they're just like, they're in the water together, hanging out. Okay, tell me about this one. Name this one. Calcium chloride in CaCl2. You can see the 2 chlorines there, and you already knew that because calcium drops the 2 down. And so what does that look like in water? Ca charge 2 plus, right? And Cl minus and Cl minus. Do you see that? We're just dissecting it. We're just chopping it off. We're just breaking it apart. Okay, those are ionic ionics. You can see that they break into 2 ions, 3 ions. Who do you think would be a stronger electrolyte? Meaning allow for more electricity. So these things by themselves do not make electricity. They allow for electricity to flow through them, but they don't make electricity. That was a big misconception on our cartoons we drew. They are not just magical, like, hey, let's make electricity. They allow electricity to flow. So if I shock the water allows electricity through. Which would be more conductive, do you think? Right, calcium chloride is more conductive because it's got more ions. More ions are more electrolytes. More stuff can flow through. This is ethanol. What's ethanol's formula? Eth is 2. Ethanol. H5 OH. Good, because you said you wanted to say 6. You want to say ethane is 6, but instead of leaving all the H's intact, we take away 1 and we add an OH instead. That's ethanol. So, is that ionic or covalent? Why covalent? There's no metals, right? Is that being the way it is? I know most of this looks to me like it's an equal distribution throughout. Equal electrons kind of distribute everywhere. There's a little OH group right there, but it's not very big, so we might just ignore it for a moment. If I tell you that's equal distribution all the way around, is that polar or nonpolar? Nonpolar. So is nonpolar? Oh, is nonpolar going to dissolve in water? No. So it's going to be a layer. There'll be water on the bottom, ethanol on top. Okay. Well, time flies and you have fun. Do you guys finish as much? I'll answer that tomorrow, okay? Yeah. Yeah. Hey, Scott, on the way, can you grab the clock off the wall? Can you grab the clock down here? Because my AP students grabbed it off the wall. Thanks. Leadership. Okay. I wonder if you're pretty good at everything. So you have to make up your test. You can make up your test. On
Oh, are we? When would be the best day?
Are you helping too with reading a day? This week. Thank you.
Like after school or during church?